Hi everyone. Today I'm very glad to do a presentation for teaching outline to introduce the simply supported beam to students, incorporating hand calculation, computational assistive techniques, and lab sessions. Now let's start. Beam structures are everywhere. They are used in bridges, cranes, even in parts of the International Space Station. And for good reason. They allow us to create strong structures while using materials in a very efficient and cost-effective way. So today I will talk about the fundamentals of simply supported beam and the methods for calculating reactions. So we have question, what exactly is a beam? According to the first item, a beam is horizontal load-bearing elements in a structure. So take a look at this bridge. For example, simply supported beam consists of one spine with one support at each end. The loads are to the two vertical forces on each end of the bridge. The beam in the picture below only carries loads acting in its plane, and so we can analyze it as a two-dimensional structure. There are two important assumptions we need to be able to make for structure to be considered as a simply supported beam under uniformly distributed load, namely UDL. First, we need to be able to assume that load Q is distributed throughout the beam span, having constant magnitude and direction. The second assumption we need to be able to make is that the ends of these beams are free to rotate and have no moment resistance. For the simply supported beam, it sustains shearing and bending. There are a lot of different ways to build a simply supported beam, such as supporting structure in construction work and then bridge element. To be able to design or analyze a simply supported beam, we need to be able to determine the reactions. Let's consider the two supports. First is the pin joints. So you can see in the diagram, you imagine that this part of the beam is allowed to rotate. There's no resistance to rotation in this pin joint, but it does provide a resistance to forces in the vertical and horizontal sense. Let's look at the other one. So on the other side, we had a roller support, similar in the sense that there are no moments at their joints, and there's no motion in the vertical sense, and it is considered to move in the horizontal sense. So there's only one force in the free body diagram FBD. To introduce the concept of reactions in a simply supported beam under UDL, we should create a free body diagram for the beam and do different equilibrium check for the hand calculation. Let's work through the steps for calculation reactions for simply supported beam under uniformly distributed load. First, let's calculate the moment at end A and B, then draw the free body diagram, and then determine the reaction forces using our equilibrium equations. Here's an example. Here we can see we have a beam of 8 meters with uniformly distributed load of 6 kilonewton per meter, acting on 8 meters. Let's start the calculation of the moment at point A. This is point A, and if we calculate the moment at point A, then the sum of moment acting on A will be 0. And these are the assumptions that we will consider the clockwise moment as positive and the anti-clockwise moment as negative. If we consider the moment at point A, then this uniformly distributed load will bend the beam in clockwise direction. So let's calculate the moment at point A. The sum of moment will be 0, and this plus sign shows that this bending moment is in clockwise direction, and the minus sign shows that this support will resist the moment in anti-clockwise direction. So let's start the calculation. W is a uniformly distributed load acting on 8 meters of length and acting from the centroid. Here you can see we have a rectangular load, so the centroid will be the center of the beam, L by 2. So we can get the result RB equal 24 kilonewton from the equations. We can also get the formula for reaction RA and RB equal uniform load W times half of the beam length L. Similarly, we can calculate the support reactions at point B. If we consider the moment at point B, then this will bend the beam in anti-clockwise direction. So this is the equation again for calculating RA. RA is 24 kilonewton as well. Let's check for equilibrium. For that, we will consider the condition of equilibrium is the sum of all the forces acting in vertical direction, or we call that direction would be 0. It means our calculation is correct. And here is a free body diagram. Now we will write the shear force equation and also draw the shear force diagram. Look at the shear force equation. V is the shear force and the x is wherever we want to calculate the shear. X is the distance to the target point. In this example, we will calculate the shear at 3 points. First of all, we will calculate the shear at point A, then at the center of beam point C, and the end point B. Let's start the calculation of shear force at point A. RA is the support reaction, and the plus sign shows it acts in the upward direction, and the minus sign shows the UDL acting in the downward direction. W is the UDL acting on X, so that point A the shear would become 24 kilonewton since X is 0 at point A. Let's draw a line of 24 kilonewton at point A. Now we will calculate the shear at the center of the beam at point C. X will become 4 meters from point A, so the VC is 0. At point B, X will be 8 meters. The shear force would be minus 24 kilonewton. The shear force equation is linear, so the shear force diagram looks like this. The upper part would be the positive and the lower part would be the negative. Let's draw the bending moment diagram. The bending moment equation is simple to learn. You just have to multiply the shear force equation with the moment arm. So RA is the reaction acting at X. X will be the moment arm, and the minus sign shows that it's in the anti-clockwise direction. So moment at point A will become 0 kilonewton per meter since X is 0 at point A. And at the center, the moment will become 48 kilonewton because at the center the X is 4 meters. And for point B, the moment is again 0 since the X is 8 at this point. So the moment at the center point is the maximum bending moment. Here we introduce computational assistive techniques for help us do the complex beam structure analysis. SAP 2000 is a powerful finite element structure analysis tool, and we can use the results in SAP 2000 to validate our hand calculation results. By incorporating FE analysis software, students can gain a deeper understanding of beam behavior, learn how to apply computational techniques to solve complex problems, and achieve various learning objectives. Here's how software can be used and its benefits. First one is visualization and interactivity. Trust analysis software provides visualization of beam structures, allowing students to observe the behavior and deformations in real time. The second one is virtual experiments. Software enables students to conduct virtual experiments that would otherwise be challenging or time-consuming in a physical lab setting. This hands-on experience enhances their understanding of how trusses or beams behave under different conditions. The third one is complex problem solving. Incorporating FE software in beam structure analysis enables students to solve complex problems efficiently. The fourth one is collaboration and feedback. Software tools can bring collaboration among students and teachers. The environment encourages active learning and fosters a sense of community in the classroom. Finally, exposure to industry tools. Many engineering companies use advanced software tools for structural analysis, including FE software. So by incorporating such tools in the classroom, students gain practical experience with industry standard software for future career. So here's the detail for simple example for tutorial. Step 1 is begin a new model in SUB 2000 and then we draw the frame objects. In step 3, we assign genre constraints and then we assign load conditions. Then we run the analysis. Finally, we can get the force stresses results. Let's have a brief introduction for the lab sessions. A three-dimensional beam is tested under different loadings and load deflection and reactions are measured. These latter derived results are compared to the results from analysis using a two-dimensional model of the beam. Thus, comparison can be made between the model of the beam and the performance of the actual beam, and therefore some examination of the validity of some of the assumptions made in forming the model can be examined. In performing the lab work, each student is introduced to a number of types of equipment and associated concepts. These are strain gauges and the measurement of force, deflection meters, load cells, load displacement relations, and the use of experimental calibration to obtain indirect measurements of one parameter, while the direct measurement of another parameter. Before every lab work, we should do risk analysis for every student's safety. Especially notice injury from toppling carrying equipment. The performance of the lab work requires three parts. Work before coming to the lab is a pre-lab work. Lab during the lab is in-lab work. And the work to be done after leaving the lab is post-lab work. The details for this lab work and equipment setup, experimental procedures, the lab report, worksheets will be introduced later. So that's all. Thank you.